Hello, welcome back to Sri Sai Tech Edu YouTube channel. Read, Lead, Success. I've started with the network analysis and control systems. You have done with the module 1 first chapter in the previous videos, and module 1 second chapter also has started. We have done with already. I've already uploaded 3 theorems. Now we are going to start the next theorem in this video. In the network theorems, I've already done superposition theorem, Thevenin's theorem, Norton's theorem. Now we are going to start with maximum power transfer theorem. This is the last theorem of the module. We will see now. Maximum power transfer theorem. Statement. What is the statement? Maximum power will be delivered by a network to an impedance ZR if the impedance of the ZR is the complex conjugate of the impedance Z of the network, measuring looking back into terminals of the network. What it means? Maximum power will be delivered to the ZR, that is load impedance. Maximum power delivered to this ZR if the impedance of this ZR is a complex conjugate. Complex conjugate means A plus IB form, means A plus IB or A plus ZB. A plus JB. A will be the real part, B will be the imaginary part. Complex conjugate. Complex conjugate of the load resistance ZR or load impedance ZR of the network, measuring looking back into the terminals of the network. We were looking back into these terminals of the network, that is A and B. That is the maximum power transfer theorem. It is a statement. Proof is also important. So we will see the proof. In proof, if finding the load current, initially we will find the load current, that is I. To get the current of this network, I is equals to total potential E V by impedance Z and ZR in series, so Z plus ZR. After that, if you see, we will write impedance Z plus ZR in terms of complex conjugate. How we will write in the complex conjugate? R plus JX. So R is nothing but RR plus R plus J into XR plus X. Here this is load resistance and load impedance. This is normal the resistance, that is for Z, R and X. Okay, we are writing in this form. After writing this, power we need to find. For finding power, what is the formula? P is equals to I square R. If you see, I is E by R plus J into XR plus X. This is I square. This is I square. If you see, we are squaring this. I square by RR plus R square plus J into XR plus X whole square. Okay, into RR. That is the RR is the load resistance. The formula is like that. I square R. The formula is what? P is equals to not IR square. It is I square R. P is equals to I square R. We'll write in that form. After writing in that form, what you will get? Z here they have mentioned where Z is what? R plus JX and ZR is RR plus JXR. See, if you multiply this J inside, what happens? This R plus JX is Z. Then RR plus JXR will be ZR. Okay. That in that way we have written. For Z and ZR separately we have written the complex conjugate. Sorry. Then for maximum power, what is the condition? The partial differentiation of this dou P by dou XR must be 0. The power with rate of the impedance XR, reactance XR should be 0. Dou P by dou XR must be 0. So dou P by dou XR, how to find? By doing differentiation, that is minus 2 into E square RR. If you see here, if you do the differentiation, you are going to get this actually. See, we want only the XR terms for differentiation. Okay. After doing the XR terms differentiation, what you will get is this. After doing the differentiation, if you check XR plus X is equals to 0 you give, then what it will be, you can make anything equals to 0. So as it is in multiplication, xr plus x will be equals to 0. This term goes this side, it will become 0. This term also goes this side, becomes 0. So it will be, we will be remaining with xr plus x. So xr plus x is equals to 0. xr is equals to minus x. So what it means, you can substitute xr equals to minus x in this equation, so that you can remove that imaginary part. The reactance of the load impedance is of opposite sign to the reactance of the source impedance. The load impedance is the opposite sign of the source impedance. This this z is nothing but source impedance. So reactance in the impedance itself, the reactance of the load impedance is calculated. So the reactance of the load impedance is of opposite sign to the reactance of the source impedance. Okay. Then now we will substitute xr is equal to minus x in this equation and see what will happen. Putting xr equals to minus x in that equation, what happens is the complex conjugate, the j term whatever is there, that is eliminated. Why? Because x and minus x, it becomes 0. So it will be eliminated. For maximum power, what we will we need dou p by dou rr is equals to 0. So if you differentiate this equation, what you will get is this. Why? Because it is u by v formula. If you we need to differentiate v into differentiation of du by dx, du by dx in that form, minus u into dv by dx by v square. I hope you know this formula, but then too I am writing, you will be learning this formula differentiation in the maths actually. Here you need to do differentiation. After doing differentiation, you need to equate it to 0 for maximum power. After equating into 0, if you calculate this, you will get e square r into rr plus r minus 2 e square rr is equals to 0. And if you equate this, and there will be cancellations happening here. After cancellation, rr will be equals to r. If you calculate this, you will understand. If you calculate this equation, you will understand rr is equals to r. After getting rr equals to r, what it means, we can make a conclusion therefore that xr is equals to minus x and rr is equals to r. That is, load resistance and the source resistance equals, and load reactance and is equals to the opposite sign of the source reactance. That is the conclusion what we got. Then maximum power will be transferred from source to load. If these conditions happen, then the maximum power will be transferred from source to load. For maximum power transfer, load impedance ZR should be complex conjugate of the internal impedance Z of source that is ZR is equals to X conjugate. Okay, this is another condition. Then the maximum power transfer will be, if you substitute RR is equals to R. In the place of R, if you substitute RR, R equals to RR anyways, then you will get what? P is equals to E square by 4 RR. Okay, this is the maximum power transfer of that network, what it is shown in the previous slide. So the efficiency is 50% here. Okay, this is the proof. This is the proof. If they ask for maximum power transfer proof, you need to first write the statement and draw the diagram and explain this in steps. These all equations, and write till here, so that you will get our good marks. We'll go to sums now. The circuit shown in figure is a model for the common emitter bipolar junction transistor amplifier. Choose the load resistance so that the maximum power is transferred to it from the amplifier, and calculate the actual power absorbed. They are asking for the maximum power transferring at this load resistance, that is for RL. What is the RL value required? What is the load resistance required so that the maximum power is transferred to the amplifier. We'll check how to do. If you see the diagram, you need to first to get RL. Here we are using Thevenin's theorem. Here for using Thevenin's theorem, what we do, we open circuit. First the open circuit the terminals. Then here we are finding first RTH. For finding RTH, what we'll do, we remove the voltage sources. So I've short circuit the voltage source. Then we have written the other circuit as it is. As you can see, we first determine the Thevenin equivalent resistance RTH. So, since V pi is equal to 0, why V pi is 0? Here actually there was a voltage source initially present. But as we short circuited to find the Thevenin's equivalent resistance, there is no source to give the energy here or the voltage. So, this V pi will be 0. As V pi is 0, this also will become 0 because it is dependent source. So, 0.03 into V pi they have given. So, V pi is 0, then this source also will be 0. We are left with only 1 kilo ohm. So RTH will be 1 kilo ohm. So this much this will also become 0. This is also 0. You will get RTH is equals to 1 kilo ohm. We got RTH now. Then is example continuation. After that you will bring back the voltage source to the will connect back. Then we will find from the open terminals VOC, that Thevenin's voltage. For finding Thevenin's voltage, what we will do is first we find VOC across the terminals. To find VOC across terminals, what is that? Current I into R we need to do. If you see here, for finding VOC at these terminals, what are the two things you have? 0.03. That as the current is in opposite direction, what we will do? Minus 0.03 V pi into 1000 is the resistance. I into R. You will do. After that, we want V pi value. Now, why? Because we don't know V pi value. To find V pi, use voltage dividing rule. For finding V pi across 5 kilo ohm, what we need to do? As we can see that 17 kilo ohm and 5 kilo ohm are in parallel. So you find it that, then you will get 3864 as the resistance. After finding this, what you want V pi value across this. V pi value across this is equals to the total voltage, whatever it is there, 2.5 into 10 power minus 3 sine by 10 power minus 3 milli is given, 10 power minus 3 sine 440 into the voltage where you want the V pi, that is 3864 by 300 plus 3864. Okay, then you will get the V pi value. This is the V pi value. That sine 440t will be like that itself. You multiply this and this, then you will get 2.319 into 10 power minus 3 sine 440t. You got now V pi and RTH. Now what we want? Power transfer. So VOC is equal to VTH, that is equals to VOC. We got now V pi. Now what we will do? We will put this V pi value here to find VOC or Thevenin's voltage. If you put back that and multiply with minus 30, you will get minus 69.6 sine 440t millivolts. So maximum power is, we have the formula for maximum power. Initially we have studied in the proof is that is voltage square by 4R. Okay, voltage square by 4R. So you put the values VTH and RTH, then do the calculation. You will get P max as 1.211 sine square 440t microwatts as the power transferred, the maximum power transferred required for the load resistance RL. This is what the how to solve the question for maximum power transfer. We will see the next question. For the circuit drawn in figure, determine the Thevenin equivalent connected to R out. Choose the R out such that maximum power is delivered. First we need to find Thevenin equivalent connected to R out. Thevenin equivalent is what? VTH and RTH. Then we need to choose R out with that, so that it will give the maximum power to that R out. So first we will open circuit the terminals. Then we see into the terminals and find the Thevenin's voltage. For finding Thevenin's voltage across this, we can use voltage dividing rule or apply KVL. By applying KVL, what we will do? For the mesh 1 you will write that as minus 3i minus 4 minus 2 minus 2i is equals to 0. You will get I is equals to minus 1.2 amperes. If you don't know how to do KVL, I have already done the videos based on mesh analysis and nodal analysis. You can check them. After doing, after getting I, what we can do, we can find VOC at terminals easily. That is 2 plus 2 into I. Why? Because we want voltage across this. Voltage is what? I into R, I into 2 plus 2. After substituting the I value, you will get minus 400 millivolts as the Thevenin's voltage. Now Thevenin's resistance is, you remove this voltage source and short circuit, you will get 3 and 2 are in parallel. 3 and 2 parallel means 3 into 2 by 2 plus 3. RTH will be equals to 1.2 ohms. After finding this, we need to tell what is the R out value so that maximum power can be transferred. As we can say that by choosing R out is equals to Thevenin equivalent resistance 1.2 ohm, so that the maximum power is delivered to it. That's it. Just we will use the Thevenin equivalent, the same procedure, and tell that the RTH is only the required R out, so that the maximum power will be transferred. Okay. Next question. Study the circuit. Determine the Norton equivalent connected to the resistor R out. Norton equivalent they're telling to find. Then select a value for R out such that maximum power will be delivered to it. Select a value for R out. We need to find R out so that the maximum power will be delivered as like a previous sum. Here they are asking for Norton equivalent. Here I am telling once again is that maximum power transfer is linked with Norton's and Thevenin's theorem. So you should know Thevenin's and Norton's. If you don't know how to do Norton's and Thevenin's theorem, then please watch my previous videos. I've separately did for Thevenin's and Norton's, so you'll understand how to do. And even in Thevenin's and Norton's also superposition is used in some questions. So superposition, so these all theorems are interlinked. You should know the theorems to solve. So we will see how to solve this sum. For Norton equivalent, what we will do, we will short circuit first. We remove that the load resistance, that is R out, and we'll short circuit. And what they want, Norton equivalent connected to resistor. Norton equivalent we want IN. For finding IN, what we will do, apply KVL to mesh 1. By applying KVL, you will get minus 4000 plus minus 1000 I1 minus 2, then minus 2000 into I1 minus I2. Why? Because with respect to I1 we are doing mesh 1, so I1 minus I2 equals to 0. You will get the equation like this. Then after that, apply KVL to mesh 2. Applying KVL to mesh 2, you will get minus 2000 into I2 minus I1 plus 2 and minus 3, that is equals to 0. You will get second equation. Solving using Calci or Cramer's rule, it's your wish. By calculating, you will get I2 is equals to IN. No, that is nothing but we find Norton's equivalent current at the short circuit itself. So I2 will be the Norton's current. I2 is equals to IN is equals to 400 milliamperes. After getting this, what we want? We want the resistance R out. To find the resistance, remove the current voltage sources by short circuiting it. Then if you see it, 1 kilo ohm and 2 kilo ohm are in parallel. By using parallel, how to calculate the resistance, 1 kilo ohm is parallel, 1 kilo ohm into 2 kilo ohm by 1 kilo ohm plus 2 kilo ohm, we will get 667 ohms. Whatever the RTH is caused is the maximum power can be transferred, so that R out will be equals to RTH. So whatever RTH you will get, that will be the resistance required for the load resistance, so that maximum power can be obtained. The same value will write, and you will write the sentence. What is that? Maximum power is obtained by R out is equals to RTH. Okay, this is the answer. Then next question. For the circuit of figure, what value of RL will ensure it absorbs the maximum possible amount of power? We want RL so that it absorbs the maximum amount of power. Nothing but what we will do, we will open circuit the current source, and we open circuited this current source and short circuited this voltage source. Just find the RTH. How we will find RTH? Here 3 and 2 are in parallel. Again these 3 and 2 are in parallel. Again these in turn are parallel with 5 ohms. I'll show you how to calculate now. See, 3 parallel to 2 parallel to 5. All are parallel. So you will get as 9.67.7 milli ohms. Nothing but how you will calculate R equivalent. Initially there are videos, but once again I am telling you, R equivalent equals to 1 by 3 plus 1 by 2 plus 1 by 5. You will look parallel, no? After doing this, whichever value you will get, you will find R equivalent by inversing it, so that you will get R equivalent value. Okay, RTH is 967.7 milli ohms. Then setting RL is equals to RTH. This RL, that RL, they want RL. What is the RL? Load the RL. Here RL should be how much resistance, so it will absorb maximum power. Is that the total resistance what you got in the network, that is 967.7 milli ohms. If that is there in the RL, so maximum power will be delivered to that resistance. That's it. So we are done with the superposition theorem, Thevenin's theorem, Norton's theorem, and maximum power transfer theorem successfully. And module 1 is also successfully completed. If you have not watched my previous videos, please do watch. If you have any doubt in the sums, please do comment in the comment box. I will reply and I will try to solve them. If you have any other doubts, if you want any other topics also to be told, if you are not understanding, please tell me. I will do that and upload. For now, I am stopping the video. From the next videos, we will start with the module 2. Now we are done with basic circuit elements and network theorems also. Module 1 is completed successfully. Thank you. From Sri Sai Tech Edu YouTube channel, Read, Lead, Success. Keep reading.